Hello and welcome to another physics tutorial. Today we'll be talking about kinematics in R3 or 3 dimensions, and this problem right here revolves around a particle's movement, which is given by an equation, and we'll have to deduce some things about that particle. All right, so let's dive right in. An electron's position is given by r equals 3t in the x component minus 5t squared in the y component and plus 2 in the z component, with t being in seconds and r being in meters. So we've got 4 parts to this problem, and let's first take a look at the first part. Oops, sorry about that. Alright, let's take a look at the first part right here. So it asks, in unit vector notation, what is the electron's velocity v of t? So we're given an equation that gives us position, and we're asked to find the equation in terms of velocity. So what we can do is, from calculus, we can basically recall that, and this is for part A, we can recall that the derivative of position is equal to velocity, so we can write the velocity of the particle at a certain time is equal to the derivative of the particle's position over time. And so we have this equation of position here, and so what we can do is we can take its derivative component-wise, and that's how we'll get our velocity, the electron's velocity. Alright, so here we have v of t is equal to r prime of t, which is equal to, and let's do this derivative component-wise, 3t, we get just 3 in the x direction, minus, now this is a power rule here, t is raised to the second power, so that's minus 10. Bring the 2 down, multiplied by 5, and we're simply left with t, and that's in the y. And then we have a constant in the z, so it's going to just be 0 in the z direction. And that is our derivative of position, which gives our velocity equation. Alright, so now, using that, part B, we're going to have to use that further, and part B asks, what is v in unit vector notation at t equals 9 seconds? So we're asked to find the velocity of this electron at t equals 9 seconds. So essentially what we can do is we can write v of 9 is equal to, and we simply plug in values for this equation. We get, and it's asked in unit vector notation, so we'll leave it in vector notation. So because there's no t here, this is simply 3 in the x direction, minus, now we have a t here, so it's 9 times negative 10, which is minus 90 in the y, and then we just have 0 in the z direction. And that is the electron's velocity at 9 seconds. So now in part C, it asks for the magnitude of the velocity at 9 seconds. So here we have a description of this electron's velocity in terms of its components, and to find the magnitude in R3 space, we just recall that, and I'll write this out for a reference, that magnitude in R3, this is 3 dimensions, is equal to, and it's actually, the notation is like this, of some unit vector, which is equal to, it's the square root of each component squared. So for reference, I'll, in this case, I'll write x hat squared plus y hat squared plus z hat squared, and this will give us the magnitude. So now, for our case, we're asked to find the magnitude at 9 seconds. So simply what we can do is we can, and let me go back to this, we can give that magnitude of the velocity given in this notation, evaluated at 9 seconds, is equivalent to And now we have the x component squared, so that is the square root of 3 squared plus the y component squared, which is negative 90 squared. And I'm observing all significant figures in this case as well. Oops, that was not good. Let me put that better. And then lastly, we have 0 squared, which I just wrote that for reference. And so evaluating that, we get approximately, and I'll just change the color here, we get approximately 90.04999 meters per second. And that is the magnitude of the velocity at that point. And so now we're on the last part, D. And D asks, what angle does V make, this magnitude of V, with the positive direction of the x-axis at t equals 9 seconds? So in order to do this, there's many ways to do this, but I guess the approach that we can take is the conventional trigonometric approach. So I'm going to draw the velocity, the components of the velocity. So I'm going to take this equation right here into analysis, and I'll simply I'll just draw the xy plane and give it as hold on, here's x and here's y. Oops. You know what? Let me move that to the top just for better reference. All right, and so the components of the particle at t equals 9 is we have 3 in the x, so this is going to be 3. And now I just want you guys to know that this image is not to scale. So I'm going to draw it the best I can. And then in the, and I should, let me just write this in for you. Here's 3. And then the y component is negative 90. So we go all the way down. And this is 90x. And so what we're left with is, and this resulting magnitude is given as such right here. And so we can find this angle right here. They're asking for this angle, which I'll label as, we'll call this angle theta naught. They want that angle theta naught in relation to the x-axis, in the positive direction of the x-axis, at t equals 9 seconds. So what we can do is we can use trigonometry, specifically the tangent inverse, because we have the x and the y component. And I'll just, for clarity's sake, I will draw the y component moved over right there. So this is also 90 right here. This is 90y, and let me just fix that. That's a y. So that's 90y. So now what we can do is we can solve for theta naught using the arctangent. And so we have that tangent inverse of, and the tangent inverse is opposite over adjacent, so it's negative 90.00 divided by, and we have 3.00, and this yields a theta naught of about negative 88.091 degrees, and that's given downwards in this direction, the negative direction. And additionally, I just wanted to show you that you can solve this using a whole array of trigonometric conventions. So you can additionally write it as the sine inverse of, and for sine inverse it would be, what it would be is it would be this component, the y component here, against the magnitude component. So magnitude of v at 9 seconds. And so that sine inverse will be the opposite side, negative 90, divided by 90.0499, and evaluating that, we get theta naught is also about negative 88.091 degrees, the same exact angle. So I just want to thank you for watching. I hope you enjoyed this video, and I hope it cleared up any troubles that you were having with